Right now, while you are listening to this, you are being carried around the Milky Way by something you cannot see. It does not glow, it does not shine, it does not even have a surface you could point to, and yet it quietly controls the motion of hundreds of billions of stars, including our sun, like a conductor hidden behind a curtain. If this thing suddenly vanished, the galaxy would not just look different, it would unravel. The strangest part is that we are not guessing anymore. We have evidence so sharp it feels unfair. Stay with me, and if you want more investigations like this, please like and subscribe. Our galaxy has a centre, and that centre has a weight. Not a poetic weight, a measurable, gravitational, undeniable weight. About 26,000 light years from us, in this direction of the constellation Sagittarius, there is a compact object so massive that the stars near it move like they are on invisible rails. Astronomers call it Sagittarius A star. That name sounds almost gentle, like a star you might wish on. But it is not a star. It is the dark heart of the Milky Way, a supermassive black hole. That phrase can feel like science fiction, supermassive black hole. It sounds like a monster that eats everything and ends the story. But reality is weirder and more precise. This is not a cosmic vacuum cleaner roaming the galaxy. It sits at the centre and the galaxy moves around it. The Sun, along with every planet you have ever heard of, is part of that motion. We are in the suburbs, far from the downtown chaos, and that distance is probably the reason you get to exist at all. Still, the fact remains. Our cosmic address includes a black hole, right at the place where the Milky Way keeps its balance. So here is our problem. How do you prove an invisible object exists when the very definition of it is that light cannot escape? You cannot take a normal photograph. You cannot look through a backyard telescope and spot it. Between us and the centre, the galaxy is packed with dust and gas that blocks visible light like a wall of smoke. For most of human history, the Milky Way looked like a bright band overhead, and the centre looked like nothing special. No sign, no warning, just stars. Then technology started cheating in the best way. We learned to see the universe in wavelengths your eyes never evolved to handle. Radio waves, infrared light, X-rays, and when we did, the galactic centre stopped being a blank spot and became a crime scene full of clues. Something was radiating energy, something was stirring gas, something was sitting there, heavy and compact, doing gravity at an almost insulting level. But suspicion is not post-proof. To prove it, astronomers needed a kind of evidence that nature cannot fake. They found it in motion. Near the centre there are stars that whip around an unseen point with ridiculous speed. Not a little faster than normal. Faster in a way that forces you to stop thinking like a human and start thinking like physics. Some of these stars complete an orbit in a human lifetime. That is already wild. Then you learn their orbits are not neat circles. They are stretched, elongated paths that swing close to the darkness and then slingshot back out. At their closest approach, they move thousands of kilometers per second at a noticeable fraction of the speed of light. When a star does that, it is basically screaming the mass of whatever is pulling it. This is one of the most beautiful tricks in science. You do not need to touch the object. You do not need a piece of it in a lab. You watch what it does to everything around it. Gravity is a confession you can read from a distance. Track the orbit, measure the speed, and the math forces the answer. And the answer at the centre of the Milky Way is brutal. About 4.3 million times the mass of our Sun is packed into a region so small and dark that no known cluster of ordinary objects could survive there without collapsing. There is no stable pile of normal stars that can hide that much mass in that tiny space. There is only one kind of thing we know that fits, a black hole, but even that left a discomforting gap. We had the mass, we had the location, we had decades of stellar orbits that nailed the case shut. And still, part of the human brain wants the same thing it always wants. A picture, a direct sighting, something you can point at and say, there, that is it. And that craving is not childish. It is practical. A picture is a test. If the image matches what general relativity predicts, then our best theory of gravity survives one of the harshest exams in the universe. If the image does not match, then physics has a serious problem. In 2022, we finally got that picture. It was not taken by one telescope. It was taken by a planet pretending to be a telescope. The Event Horizon Telescope is a network of observatories spread across Earth that coordinate to act like a single instrument with an Earth-sized baseline. That trick lets it see incredibly small details, the kind of detail you would need to spot a tiny ring of light around a shadow from tens of thousands of light years away. And the target, Sagittarius A star, is especially cruel. Compared to other supermassive black holes, it is relatively small, which means the material around it changes fast. Imagine trying to photograph a whirlpool where the water reshapes itself while you are still opening the shutter, and yet the collaboration did it. The image is not a picture of the black hole itself, because a black hole does not glow. It is a picture of the light around it being bent, boosted, twisted, and trapped by extreme gravity. A bright ring of hot plasma, a dark center where light cannot come back. A silhouette drawn by the warping of space and time. That image is going to be one of our main characters, but it is not the only one. Over the next parts, we are going to meet the stars that race near the abyss, the strange dusty objects that look like clouds but act like stars, and the magnetic fields that may be threading the region like invisible wires under tension. We are also going to face a paradox that sits at the edge of every black hole, the question of what happens to information when something falls in, and whether the universe keeps its own records or silently deletes them. But before we run toward the deepest mysteries, I want you to feel something simple and very real. Sagittarius. A star is not an abstract concept. It is not a distant curiosity in some random galaxy. It is the gravitational center of the system you live inside. The sun orbits it. We orbit with the sun. Every human story has happened during a tiny fraction of a single galactic lap, while this black hole has been sitting there for billions of years, mostly quiet, occasionally flaring, shaping the central region, and likely having violent outbursts in the past that left scars on the galaxy we can still see today. So the question of this series is not just what is Sagittarius A star. The question is what its existence tells us about how galaxies form, how gravity behaves when it is pushed to the limit, and how much of reality is hidden behind horizons we may never cross. The Milky Way has a dark heart. We're going to learn how we found it, how we measured it, and why the closer we look, the stranger it gets. When people hear black hole, they usually picture a cosmic drain that sucks in everything nearby. That mental image is dramatic, but it is also misleading. A black hole is not a roaming vacuum. It is simply a place where gravity wins so completely that the usual escape routes close. Far away, it behaves like any other object with the same mass. If you replace the sun with a black hole that had the sun's mass, Earth would keep orbiting almost the same way. The danger only becomes absolute when you get close enough that escape speed becomes greater than the speed of light. So what exactly are we dealing with at the Milky Way's center? Astronomers sort black holes by mass, because mass is the main dial that changes everything about their behavior. Some black holes are born when massive stars die, leaving behind a collapsed core with a few to a few dozen times the mass of the sun. Those are stellar mass black holes. There also appear to be intermediate mass black holes in the wild, rarer, heavier, sitting between star scale and galaxy scale. Then there are the monsters, supermassive black holes. These can be millions or billions of solar masses, and they sit at the centers of most large galaxies like they own the place. Sagittarius. A star belongs to that last category, even though it is modest by supermassive standards. Its mass is about 4.3 million times the mass of our Sun. Let that number sit in your chest for a second, because our brains hate it. The Sun already dominates our entire solar system. Roughly 99.8% of the solar system's mass is the Sun. Everything else, every planet, moon, asteroid, comet, and dust grain combined, is about 0.2%. Now imagine taking 4.3 million suns and putting them into one object. Now comes the part that feels like an insult to common sense. Even with all that mass, the region that marks the black hole's boundary is not huge. The boundary has a name, the event horizon. It is the point of no return. Cross it, and every possible path you can take leads deeper in. Not because something is pulling you like a rope, but because space and time are curved so extremely that the future direction points inward. In the simplest picture, the event horizon of Sagittarius A star has a diameter of about 24 million kilometers. That is small enough to fit comfortably inside the orbit of Mercury. This is where you have to rewire intuition. We tend to equate more mass with bigger size, like piling more clay onto a ball. Black holes do not work like that. Their size is not set by a surface made of matter. Their size is set by geometry, by how much space and time have been warped by mass. A more massive black hole does have a larger event horizon, but not nearly as large as you would expect if you're thinking like a planet or a star. A black hole can be outrageously massive and still have an event horizon that, on a cosmic scale, is basically a pinprick. That compactness is the entire story. 4.3 million solar masses inside something smaller than Mercury's orbit. If you're trying to imagine what that means physically, you might immediately ask about density. You might imagine matter crushed into a ball like the densest rock in the universe. But here is the strange truth. The event horizon is not a wall, and it is not a container full of material you can scoop. It is a boundary in space-time. Outside, escape is possible. Inside, escape is not. The mass that creates the black hole can come from collapse matter, from energy, from everything that fell in over the black hole's history. But the event horizon itself is not a chunk of stuff. It is a line the universe draws when gravity becomes too steep. Still, the fact that this boundary is so small tells you something unavoidable. Whatever is creating this gravity is concentrated into an extraordinarily compact region. If it were a cluster of normal stars, they would collide, merge and shine. If it were a dense ball of dead stars, their gravity would make them fall together and collapse. If it were a cloud of gas, it would radiate, heat up and form stars. Every ordinary alternative either glows, explodes or falls apart under its own physics. The simplest thing that can hide that much mass in that little volume is a black hole. Now, one more concept matters here, because it explains why black holes feel so alien. There is a difference between being massive and being extreme. The Sun is massive, but you can orbit it safely at Earth's distance. Sagittarius. A star is massively more massive, but it is also far away from us, and distance is a mercy. Gravity drops fast with distance. At our location in the galaxy, the black hole is not tugging on you like a monster under the bed. Most of the time, the gravity you feel is Earth, then the Sun, and then maybe the Moon, then everything else. Sagittarius. A star matters to our overall orbit around the galactic centre, but it is not trying to eat the solar system. The extreme physics happens in the inner neighbourhood, close to the event horizon. As you approach, the curvature of space-time gets more intense, and your normal rules start to wobble. Time runs differently, orbits precess, light bends, and the idea of a clean, stable path becomes more like a negotiation with geometry. This is why Sagittarius A star is such a gift to science. It is close enough that we can measure fine details, but far enough that we can observe without being destroyed by the very thing we are studying. But we still have a huge practical problem. If the event horizon is literally defined by light failing to escape, then how can we ever see anything that proves it is there? Not just infer it, not just calculate it, but actually see it. That question is the doorway into the next leap, because the way we solved it is one of the most audacious ideas in modern astronomy. We built a telescope out of Earth itself, and we used it to photograph a shadow. If you tried to look straight at the centre of the Milky Way with your eyes, you would think there is nothing there. Not because the centre is empty, but because the galaxy is messy. Between us and the core sits a thick, chaotic layer of dust and gas that absorbs visible light. It is like trying to see a city skyline through 1,000 kilometers of smoke. The light is real, the objects are real, but the route to your retina is blocked. So the story of finding Sagittarius A star begins with a simple cheat. Stop using visible light. The first hints did not come as a majestic image or a dramatic discovery announcement. They came as annoyance. In the 1930s, a radio engineer named Karl Jansky was trying to understand weird static interfering with radio communications. He was not hunting black holes. He was hunting noise, but when he tracked the pattern, he found something astonishing. The static rose and fell with a rhythm tied to the sky, not to weather or machinery. A source of radio waves was coming from space, and it seemed to be strongest from the direction of Sagittarius. That moment matters because it marks the birth of radio astronomy. It is one of those scientific plot twists where the universe hands you a clue by accident, as if it cannot help itself. Over the following decades, radio telescopes became more capable, more sensitive, and more ambitious. Astronomers began mapping the sky in radio wavelengths the way earlier astronomers had mapped it in starlight. And when they looked toward the blocked heart of the galaxy, the fog started to thin. By the 1970s, radio observations had identified a particularly bright, compact radio source near what looked like the Milky Way's gravitational center. It was named Sagittarius A. Not because anyone knew it was a black hole, but because it was a standout signal in that patch of sky. A was basically a label that said this one is important. Later, astronomers would pin down an even more compact component right at the center of that radio region, a component that became known as Sagittarius A star. At this stage, the evidence was suggestive but not decisive. Something energetic was happening. Something compact was there. But the galactic center is a crowded place. There are dense star clusters, there are exploding stars, there are tangled magnetic fields and hot gas clouds and filaments of plasma. If you only have a glow on a map, you can tell 100 stories and half of them could be wrong. Science does not like maybes. Science wants a lever. So astronomers went hunting for a cleaner signal, one that could not be faked by a messy environment. And that signal was gravity acting on individual stars. Here is the catch. You cannot easily see those stars either, not in visible light. But dust that blocks visible light is kinder to longer wavelengths. Infrared light can pass through more of that dust, like a flashlight beam that cuts through fog better than a candle flame. So the strategy became clear. Look in infrared. Pick out individual stars near the core, track their positions precisely over years, watch them move, then let gravity do the talking. This is harder than it sounds. Imagine trying to track a single firefly in a stadium full of fireflies through a wavering layer of Earth's atmosphere that smears every point of light into a wobbling blur. That blur is not a small problem. For the precision needed, it is the main enemy. Even the best telescope is useless if the atmosphere turns the image into jelly. The solution was a technological magic trick that feels like it belongs in a spy movie. Adaptive optics. In plain language, it is the system that measures how the atmosphere is distorting the incoming light, then rapidly reshapes a mirror to cancel out that distortion in real time. It is like noise-cancelling headphones, but for starlight. Without adaptive optics, you see a smear, that you see crisp points again, and suddenly tracking becomes possible. Once astronomers could see the central stars clearly in infrared, the galactic center stopped being a vague glow and became a stage full of actors, and the actors were moving fast. At first, you might expect the stars at the center to drift slowly, like distant lanterns, but that is not what appeared. Some stars were racing, not across the galaxy, but around a specific invisible point, swinging in tight arcs, accelerating near closest approach, then whipping away. The shapes of their paths were not random. They were orbits, real, repeatable, mathematically describable orbits around something that did not shine. And every orbit is a measurement device. The tighter the orbit, the stronger the gravity. The faster the motion, the greater the mass inside the orbit. With enough data, you can calculate the mass of the unseen object with astonishing precision. Not a guess, not a vibe, a number. This is when the story flips from suspicion to certainty. Because once you track those stars for long enough, the alternatives collapse. You can try to explain the orbits with a cluster of neutron stars or a swarm of dead objects or some exotic pileup of matter. But those explanations fall apart under basic physics. They either would not stay stable for long, or they would glow, or they would collide, or they would collapse into a black hole anyway. So the core question becomes sharper, and honestly more thrilling. If there is an object at the center that is massive enough to whip stars around at these speeds, and compact enough to fit inside a region smaller than Mercury's orbit, and dark enough to avoid being seen directly, then what else could it be besides a black hole? By the time this approach matured, the galactic center was no longer just a mysterious radio source. It was a precise gravitational laboratory. The stars were acting like test particles in the most extreme environments in our local universe. And the measurements were not just consistent with a supermassive black hole, they practically demanded it. In the next part, we are going to meet the most famous of these stars, the ones whose orbits became the smoking gun. We are going to talk about just how fast they move, how close they get, and why their motion forces relativity to step onto the stage. Because once you are watching stars move at a noticeable fraction of the speed of light, Newton is no longer enough, and Einstein starts whispering into your equations. Once you realize the galactic center is hidden behind dust, the hunt becomes a game of patience and precision. You do not chase the monster directly. You watch its victims, or in this case its neighbors. You watch stars that live dangerously close to the deepest gravity well in our galaxy, and you ask a simple question. What kind of invisible object could force a star to move like that and still remain dark? In the 1990s, two major teams committed to a long, stubborn campaign that changed astronomy. One team was led by Andrea Ghez at the University of California, Los Angeles. Another was led by Reinhard Genzel at the Max Planck Institute. Their plan sounded almost boring on paper. Take repeated infrared images of the galactic center, identify individual stars, track their positions over years, then do it again and again and again, but the execution was brutal. The stars near the center are packed into a tiny patch of sky. Earth's atmosphere blurs and wobbles their images. The dust dims and reddens them. The field is crowded enough that starlight overlaps like headlights in a storm. To make this work, they had to turn telescopes into precision instruments, not just big light buckets. Infrared gave them the ability to see deeper through dust. Adaptive optics gave them sharpness. It measured the atmosphere's distortion in real time and reshaped mirrors to cancel it, fast enough that the stars stopped smearing and started looking like points again. And when those points became trackable, the galaxy began to confess. The first big shock was sped. Stars near Sagittarius. A star were not drifting. They were whipping around an unseen focus with velocities that should not exist so close to the center of a calm-looking galaxy. Some were moving faster than 5,000 kilometers per second. That is not fast by human standards. That is fast by physics standards. It is the kind of speed that makes you stop imagining stars as gentle lanterns and start imagining them as projectiles in a gravitational slingshot. Then one star became the headline act. It is commonly known as S2, and it became famous for a reason. Its orbit is short enough that a human can watch a full lap within a career, roughly 16 years, and it is not a neat circle. It is a stretched ellipse that takes it far out, then swings it back in toward the darkness, where it accelerates to its maximum speed. At its closest approach, S2 comes within about 17 light-hours of Sagittarius A. That distance sounds large until you remember what the center is: 4.3 million solar masses, all focused into a region smaller than Mercury's orbit. When S2 dives in that close, it reaches speeds of roughly 7,600 kilometers per second. It is moving at a noticeable fraction of the speed of light. At that point, you are no longer doing ordinary gravity. You are doing gravity with consequences. Because when you move that fast, time itself starts acting strange. This is where the story shifts from astronomy into a full-body physics experiment. Special relativity says that clocks run differently for objects in motion. General relativity says clocks run differently in strong gravity. Near Sagittarius. A star, both affects matter at the same time. Light from S2 is affected by the star's speed and by the depth of the gravitational well it is climbing out of. Its orbit should not behave exactly like a perfect Newtonian ellipse, and the closer you look, the more the universe insists on including Einstein. But the most important point is even simpler. S2 is not just one dramatic star, it is part of a whole population. As instruments improve and observations stretched across more years, astronomers identified more stars in tighter orbits. Objects like S29 push even closer, and then there is the jaw-dropping class sometimes described as the 4714 family, with orbits that get so tight and so fast that the numbers start sounding like science fiction. In recent years, astronomers reported stars in this group reaching speeds approaching about 8% of the speed of light, on the order of 24,000 kilometers per second during close passages. At those speeds, you're watching a star skim the edge of the most extreme environment we can study up close. It is like watching a sprinter run along the rim of a volcano, except the volcano is space-time itself. Now comes the part where the detective story becomes almost unfairly conclusive. If you measure the orbit of a star, you can calculate the mass that must be inside that orbit. Not vaguely, not approximately. The math is not optional. The orbit is the evidence. With enough stars, the answer becomes a chorus, not a solo. Different orbits, different angles, different periods, all pointing to the same hidden mass. And the answer is consistent. Roughly 4.3 million solar masses are concentrated in a region so compact that it cannot be a stable cluster of normal objects. Whatever is there is dark, dense, and gravitationally dominant. That is why Andrea Ghez and Reinhard Genzel received the Nobel Prize in Physics in 2020. It was not because they had a clever idea. It was because they did the hard thing for decades, measuring patiently until the galaxy could no longer hide its secret. They transformed a suspicion into a measurement, and a measurement into a new kind of laboratory. But even after all that, there was still a human itch left unsatisfied. We had proof through motion. We had proof through mass. We had proof through relativity beginning to show its fingerprints. And still, we wanted one more thing. We wanted to see the shadow. Because the moment you can directly image the silhouette of a black hole against the light of its own environment, you are no longer only inferring gravity. You are watching space-time bend light in real time. You are testing general relativity in the most extreme way we know how, not with an equation on a chalkboard, but with a picture the universe itself provides. That is the leap we take next. Even after the stars gave up the secret, even after the mass was nailed down, even after relativity started showing up in the data like a watermark, there was still a stubborn human craving left. We wanted a picture. Not because a picture is more scientific than an orbit, but because a picture is a different kind of test. If you can image the silhouette of a black hole, you are not just measuring gravity, you're watching gravity bend light. That sounds impossible on purpose. Sagittarius. A star is 26,000 light years away. Its event horizon is only about the size of Mercury's orbit. On the sky, that is absurdly tiny. Think of it like trying to see a small object on the moon from across an ocean. Any normal telescope, even a gigantic one, will blur it into nothing. Not because the telescope is bad, but because the laws of diffraction do not care about your dreams. To resolve smaller details, you need a wider telescope, a much wider telescope. So astronomers did something wonderfully unhinged. They built a telescope out of Earth. The Event Horizon Telescope is not one instrument. It is a network of radio observatories scattered across the planet, from high mountains to deserts to polar ice. They all observe the same target at the same time, and then their data are combined using a technique called very long baseline interferometry. Interferometry is the idea that you can merge signals from separated telescopes to act like a single virtual telescope, with a diameter equal to the separation between them. When the separation spans Earth, the virtual telescope is effectively Earth-sized. That is the only way to get the resolution needed to even attempt an image of a black hole shadow. But here is the next problem. The Event Horizon Telescope does not create a normal photo. It records radio signals, massive streams of data with timing so precise that even tiny errors would ruin the reconstruction. It is like recording a symphony with microphones on different continents and then trying to line up every note afterwards so perfectly that the original music reappears. The system relies on extremely precise clocks, careful calibration, and a mountain of computation. And even if you do all of that, Sagittarius A star still tries to sabotage you, because it moves, not the black hole itself, but the glowing plasma around it. The bright ring you want to image is made by hot gas and magnetic fields swirling in the black hole's grip. Near the center, orbital times are short. For some of the innermost material, patterns can change in minutes to hours. That means imaging Sagittarius A star is not like taking a long exposure photo of a still landscape. It is more like trying to photograph a storm inside a whirlpool, while your camera is also shaking and the entire scene is behind a wall of dust. There is a reason the first black hole image the world saw was not Sagittarius A star. In 2019, the Event Horizon Telescope collaboration released the first image of black hole in another galaxy, the one at the center of Messier 87. That target is much farther away, but it is also vastly more massive. A more massive black hole has a larger event horizon, and the environment around it evolves more slowly. In a strange twist, the distant giant was easier to image than our closer, smaller, faster changing neighbor. So when the Event Horizon Telescope turned its attention to Sagittarius A star, the challenge was not just resolution, it was time. The data had to be stitched together from a target that refused to hold still. Then came May 2022. The image was released and it was honestly surreal to look at. A bright ring with uneven brightness surrounding a dark center. The dark region is often described as the shadow. It is not the event horizon itself, but the silhouette created by light being captured and bent by the black hole's gravity. Some of the light you see in that ring started behind the black hole from our point of view, then got warped around it by curved space-time and sent toward us. The ring is not a simple circle drawn in empty space. It is an optical illusion carved by gravity. And that is the point. Einstein's general theory of relativity predicts that a black hole should produce a shadow of a particular size relative to its mass and distance. It predicts how light should orbit and bend near what is called the photon sphere, a region where gravity is strong enough that light can loop around the black hole before escaping. It predicts that a bright ring of emission from hot plasma should be lensed into a near-circular structure. The details depend on the flow of gas, the angle we view it from, and the black hole's spin, but the basic silhouette is a hard prediction. The image matched those predictions, not perfectly in every tiny feature, because the environment is messy and the source changes quickly, but in the way that matters most. The size of the shadow was consistent with a black hole of about 4.3 million solar masses at the centre of the Milky Way. The overall structure looked like what relativistic simulations of an accreting black hole produce. For the second time, in a very different system, nature handed us an image that looked like a ring of fire around darkness. This was not just a pretty picture, it was a confirmation that the object we inferred from stellar orbits was indeed the kind of compact, extreme gravity object general relativity describes. It was also a confirmation that we can do something that used to sound like nonsense. We can image the neighbourhood of an event horizon, but the image raised deeper questions immediately, because the ring was not evenly bright. Some regions were brighter, some dimmer. That asymmetry is not random decoration, it carries information. Part of it can come from Doppler boosting, where material moving toward us appears brighter because of relativistic effects, while material moving away appears dimmer. Part of it can come from where the plasma is hotter or denser, and part of it can be shaped by magnetic fields, which act like invisible rails guiding charged particles in the accretion flow. This is where the story shifts from proof to diagnosis. After the first image, the collaboration continued analysing their data, including polarization. Polarization is a property of light that can reveal the geometry of magnetic fields in the emitting region. If the light is polarized in certain patterns, it suggests the magnetic field is not just chaotic static, but structured. And structure near an event horizon is a big deal, because magnetic fields are believed to control how gas loses angular momentum, how it spirals inward, and how energy can be redirected into outflows and jets. In other words, the ring is not just showing you where the gas is, it is whispering how the gas behaves, and now we have a new tension to lean into. Sagittarius. A star is quiet compared to active black holes in other galaxies. It is not devouring a steady river of matter and blasting out a brilliant beacon. But the image tells us there is still a hot dynamic environment right at the edge. Something is orbiting fast enough to glow, changing fast enough to challenge our instruments, and structured enough to suggest underlying order in the chaos. The galaxy's dark heart is not a dead rock. It is a system, a restless one. In the next part, we are going to follow that trail deeper into the magnetic story and the question of spin. Because a spinning black hole does not just sit there. It drags space-time itself around like a rotating river, and that changes what matter can do near the edge. The shadow is the doorway. What matters now is what the light around it is trying to tell us. The first image of Sagittarius. A star feels like a victory lap, a ring of light around darkness, exactly the kind of silhouette general relativity says a black hole should cast. But an image is only the beginning, because once you have a ring, the next question is unavoidable. What is shaping it? The answer is not just gravity. The region around Sagittarius' star is filled with plasma, gas so hot that atoms are stripped apart into a soup of charged particles. And charged particles do not just follow gravity, they also follow magnetic fields. If gravity is the stage, magnetic fields are the invisible rigging above it, pulling, twisting, snapping, and sometimes stealing the show. This is why the most exciting upgrade after the first image was not simply a sharper picture, it was polarized light. Polarization is like a fingerprint in the light that tells you how the electromagnetic waves are oriented. In everyday life, you might have seen polarized sunglasses cut glare off water or glass. In astronomy, polarization becomes a detective tool. When light is emitted by fast-moving electrons spiraling along magnetic field lines, the polarization pattern can reveal the geometry of those fields. It is one of the few ways we can infer the structure of something we cannot see directly. When the Event Horizon Telescope collaboration analysed polarization near Sagittarius A star, the message was surprising. The magnetic fields near the black hole did not look like a simple chaotic mess. They appeared strong and organised, with patterns that suggest structure threaded through the flow of plasma close to the event horizon. That sounds technical, but emotionally it should feel eerie. You would expect the region around a supermassive black hole to be pure turbulence, like a hurricane made of fire, with no clean lines, no order, no long-lived shape. Yet the polarization hints that there is a kind of underlying architecture, as if the chaos is happening inside a magnetic cage, and that matters because magnetic fields control feeding. A black hole does not pull matter straight in like a drain. Most matter arrives with angular momentum. It is already moving sideways as it falls. To reach the event horizon, that matter must lose angular momentum somehow. Magnetic fields can do this by linking different layers of plasma together and transferring momentum outward. In plain language, magnetic fields can act like friction with teeth. They let the inner gas shed its sideways motion and spiral deeper. They can also do the opposite. They can block accretion, choking the flow and pushing material away. In some models, strong magnetic fields can create a magnetically arrested disk, where the field becomes so dominant it partially damps the inflow and forces the system into bursts and flares instead of smooth feeding. So polarization does not just tell us what the region looks like, it hints at what the black hole is doing with its environment. Then there is the other hidden dial, one that changes the entire personality of a black hole. Spin. A black hole can rotate, and not just a little. A rapidly spinning black hole drags space-time itself around with it. This effect is called frame dragging, and it is one of those phrases that sounds like a metaphor until you realize it is literal. Space and time near the black hole are not passive background. They are being twisted by rotation. If you could hover near a rapidly spinning black hole, the geometry would try to pull you into co-rotation. There is a region outside the event horizon where nothing can remain still relative to distant stars. This region is often called the ergosphere. Inside it, space-time is moving like a current, and even light and matter must swim with the flow. Why does that matter for us? Because spin changes what orbits are possible near the edge. There is a special boundary called the innermost stable circular orbit. It is the closest distance where matter can orbit without immediately plunging in. For a non-spinning black hole, that orbit sits farther out. For a rapidly spinning black hole, it can be much closer. That means spin determines how close the brightest, hottest, fastest plasma can get before it disappears. It shapes the ring, it shapes the timing of flickers, it shapes how magnetic fields wrap and wind. It can even shape whether a black hole can launch a jet. Now comes the hard part. How do you measure spin? You cannot put a speedometer on a black hole. You have to infer it from the light and the dynamics. Polarization helps because the pattern depends on how magnetic field lines are dragged around by rotation. X-ray and infrared variability helps because hotspots and orbiting clumps have timescales that depend on the gravitational environment. The shape of the emitting region can help because the flow behaves differently depending on how close stable orbits can exist. In the transcript we are building from, the latest analyses suggest Sagittarius A may be spinning rapidly, with a spin parameter above 0.9. In plain words, more than 90% of the maximum rate allowed by physics. That is extreme. That is not a gentle turn. That is a system where space-time is being wound up tight. And spin is not just a number. Spin is history. A rapidly spinning, supermassive black hole is more likely to have grown through steady, organized feeding, gas flowing in over long periods in roughly the same rotational direction. That kind of consistent inflow adds angular momentum the same way repeated pushes on a merry-go-round speed it up. A slowly spinning one suggests a chaotic past, random mergers, misaligned gas clouds, growth that came in from many directions so the net rotation never became strong. So if Sagittarius A really is spinning fast, it hints at a long coherent diet, not just a series of random snacks. That is fascinating because Sagittarius A is also quiet today. It is not an active galactic nucleus blazing with furious accretion. It is more like a giant that is barely sipping. So why would a quiet black hole have such a wound-up rotation? That tension is one of the most interesting moods in the whole story. Sagittarius. A star might be quiet now, but it may carry a momentum from a more active past. Or it might still have an orderly inflow that is mostly being redirected outward by the magnetic fields and hot gas, leaving only a small fraction to actually cross the event horizon. In other words, it can be spinning like a turbine while being fed like a starving animal. And that takes us to a bigger point that's easy to miss. The black hole is not the only thing we are studying. We are studying an ecosystem of gravity, plasma, and magnetic fields, operating in a regime where relativity is not optional. The ring is not just a ring, it is a diagnostic screen. Every bright patch, every dim gap, every polarization twist is information about how matter behaves when it is forced to obey curved spacetime. Which brings us to the next mystery. If the magnetic fields are strong and organized, and if the black hole is spinning rapidly, then why is Sagittarius A star not producing a dramatic, obvious jet like some other supermassive black holes do? Is it launching something too faint for us to easily confirm? Is the geometry misaligned? Is the fuel supply too thin? Or is the system sitting right on the edge between quiet and active, like a campfire that could flare if someone tosses on the right log? To answer that, we have to talk about the strange calm of Sagittarius A star, and the moments when it breaks that calm with sudden bursts of light. If you only knew Sagittarius, a star from its mass, you would expect fireworks. 4.3 million solar masses should mean a powerful, hungry engine. In other galaxies, black holes of this class can become active galactic nuclei, bright enough to outshine the combined light of all their stars. They do it the same every black hole does, by feeding. Gas spirals in, heats up, and converts a startling fraction of its mass into energy before crossing the event horizon. Accretion can be more efficient than nuclear fusion, which is almost unfair. So when astronomers look at the Milky Way's center, they run into a weird mismatch. Sagittarius. A star is not blazing, it is remarkably quiet. Quiet does not mean dead, it means underfed. In the transcript we are working from, astronomers estimate it is consuming something like the mass equivalent of an asteroid only once every few centuries. For a black hole that massive, that is basically sipping through a straw. It is the cosmic version of owning a giant furnace and using it to toast a single marshmallow every 100 years. And that raises the central question of this part. Why? Because the galactic center is not empty. There is gas, there are stars, there are stellar winds, material blown off by massive stars that should be drifting through the region like a constant mist. There are clouds wandering in and being tugged around. If there is material available, why is so little of it actually falling in? One explanation is heat. Gas near the black hole can be extremely hot. Hot gas is not calm. Its particles move with strong random motion. That random motion gives the gas pressure, and pressure resists collapse. In simple terms, if the gas is too energetic, it will not settle into a neat spiraling flow. It will puff up, it will swirl, it will fight the fall. Instead of sliding smoothly inward, hot gas can be blown outward, especially if the accretion flow generates winds that carry energy away. Another explanation is magnetic fields. We just talked about how polarization suggests strong, organized magnetic structure close to the event horizon. Magnetic fields can help matter accrete by transferring angular momentum outward, but they can also obstruct inflow by creating barriers and channels. They can lock plasma into patterns that keep it from settling. In some regimes, magnetic pressure can dominate the dynamics, causing much of the incoming material to be redirected into outflows instead of being swallowed. Then there is a third factor that is easy to overlook. Most matter near Sagittarius. A star has too much angular momentum. It is orbiting. To fall in, it must lose that sideways motion. If the mechanisms that remove angular momentum are inefficient, the matter can remain in a hot, puffy flow that circulates rather than plunges. All of that would explain quietness, but then the galaxy does something rude. Sagittarius. A star flares. Not constantly, not in a way that turns it into a quasar, but in sudden, sharp bursts that last minutes to hours, detected in X-rays and infrared. For a system that seems mostly dormant, these flares are like hiccups, short bright spikes that hint at violent processes happening right at the edge. And flares are not just bright events, they are clocks, because the closer you are to the event horizon, the faster orbital times become. So when you see a flare that rises and falls on a timescale of tens of minutes, you are getting an indirect measurement of how close that emission region might be to the black hole. Fast variability implies a compact source. Something small, something close in, something being whipped around by intense gravity. What causes the flares? One possibility is that small clumps of gas fall into the inner accretion flow, heat up dramatically through shocks and turbulence, and then vanish. Another possibility is that magnetic reconnection events dump energy into a localized region, accelerating particles and producing a sudden spike in radiation. Magnetic field lines in a turbulent plasma can twist and tangle like rubber bands. When they snap and reconnect, they release stored energy fast, like a cosmic lightning strike. Either way, the message is clear. Even though Sagittarius A star is quiet in the long term, its inner environment is dynamic in the short term. Then comes an even stranger phenomenon mentioned in the transcript: quasi-periodic oscillations. That phrase sounds like academic wallpaper, but the idea is spooky. It means the brightness sometimes shows patterns that repeat on roughly regular timescales. Not perfectly like a metronome, but enough to suggest an underlying rhythm. These oscillations could come from hot spots orbiting near the innermost stable circular orbit, or from instabilities in the accretion flow that cycle through phases. They could also be tied to how the inner flow processes due to frame dragging, wobbling like a spinning top in a warped gravitational field. If you can decode these rhythms, you can infer the black hole's spin and the structure of the inner plasma. The flares become a language. Short, bright pulses are not just noise, they are the black hole's environment revealing its rules. Now, what about jets? When people picture supermassive black holes influencing galaxies, they often picture enormous jets blasting out from the poles, launching particles at near light speed across tens of thousands of light years. Those jets exist in many active galaxies. They are among the most powerful structures in the universe. Sagittarius. A star does not show a dramatic jet like that, at least not in any obvious way. But the transcript points out something intriguing. There may be evidence of a faint outflow, a weak jet or wind that is far less spectacular than those in active systems. If that is confirmed, it matters because it tells us something important. Even a quiet black hole might still produce structured outflows, just on a smaller scale. It might still be shaping its neighbourhood in subtle ways. And this is where the quietness becomes deceptive. A black hole does not need to be a quasar to matter. The central region of the Milky Way is packed with stars, gas, dust and magnetic fields. Small changes in energy injection can ripple outward. Outflows can carry energy into the surrounding medium. Winds can strip gas that might otherwise form stars. Bursts can alter local chemistry and plasma conditions. Sagittarius. A star might be quiet, but it is not irrelevant. It is more like a sleeping giant in a crowded room. And the biggest reason we care about this is not just curiosity. It is that Sagittarius A star is our nearest testbed for the physics of low accretion black holes. Most galaxies in the nearby universe are not blazing quasars right now. Many host supermassive black holes that are relatively quiet, like ours. Understanding why they are quiet and what occasional flares mean helps us understand the typical life of black holes across cosmic time. Because the cosmic truth is not constant fireworks. The cosmic truth is cycles, active phases, quiet phases, feeding events, outbursts, then long stretches of relative calm. And somewhere inside those cycles is a haunting question we cannot ignore. If Sagittarius A star is capable of sudden flares now and evidence suggests it had a far more violent past, then what controls the switch? What makes a supermassive black hole go from sipping to feasting? What kinds of events can wake it up? To answer that, we have to get closer than the flares. We have to understand the structure of the accretion flow itself, how plasma moves, how magnetic fields sculpt it, and why almost everything that approaches the black hole seems to get thrown back out. The region that feeds Sagittarius A star is often called an accretion disk, but that name can trick you into picturing something smooth and flat, like a vinyl record spinning politely in the dark. The reality is closer to a storm, a boiling, magnetized, three-dimensional flow of plasma that is constantly tearing itself apart and rebuilding. Matter is not simply falling, it is orbiting, colliding, heating, and being thrown into new paths by forces that do not care about our intuition. Start with the heat. As gas spirals inward, it loses gravitational energy, and that energy turns into motion and friction. Not friction like sandpaper, but friction created by turbulence and magnetic stresses inside the flow. Layers moving at different speeds tug on each other, twist and dump energy into the particles. The temperatures can climb into the millions of degrees. At that point, atoms cannot hold on to their electrons, and the gas becomes plasma, a charged soup that shines across radio, infrared, and X-ray light. But even calling it a disk is only partly true. Observations and models suggest the inflow around Sagittarius A is not a tidy, thin structure. It is thick, puffy, and warped. Material may arrive from different angles, fed by stellar winds and drifting clouds so the flow can tilt and bend as it settles. Instead of one clean plane, you get a complicated shape, like a whirlpool, formed where multiple rivers crash together. Then the magnetic fields step in. Magnetic fields near the black hole are not just faint traces, they can be dynamic forces that reshape the entire system. In plasma, magnetic field lines get dragged around by the flow. Differential rotation stretches them, twists them, and tangles them until they store enormous energy. If you want a mental image, picture elastic bands being wound tighter and tighter around a spinning wheel. Eventually, they cannot take the tension. And when that tension breaks, the energy does not leak out gently, it snaps. This is magnetic reconnection. Field lines rearrange into a lower energy configuration, and the difference is released fast, heating local regions and accelerating particles. In many astrophysical systems, reconnection is a prime suspect for sudden flares. It is a clean way to turn magnetic stress into light in a hurry. Near Sagittarius. A star where the field is strong and the plasma is fast, reconnection is not a rare exception. It may be part of the normal breathing of the accretion flow. Now add spin. If Sagittarius A is rotating rapidly, then frame dragging becomes more than a subtle correction. The inner flow does not just orbit. It is forced to deal with space-time that is itself being twisted. The result can be precession, a wobble of the inner accretion flow like a spinning top that refuses to stay upright. When the flow precesses, different regions rotate into and out of our line of sight. Bright patches can appear, fade, and reappear on timescales linked to the inner orbital motion. This is one reason variability becomes so valuable. The flicker is not noise, it is a probe. When you see light change over minutes or hours, you are essentially watching processes that must be happening very close to the event horizon, because only small regions can change that fast. Here is the strangest and most important point of all, for Sagittarius. A star, most of the gas that approaches does not actually fall in. It gets repelled. Observations and models suggest winds and outflows can carry away nearly everything that reaches the inner regions. Something like 99% or more of the material that gets close ends up being pushed back out rather than crossing the event horizon. Only a tiny fraction completes the final plunge. This is not a small detail. It is the likely reason Sagittarius A is so quiet. The black hole may have access to fuel, but the environment behaves like a bouncer at a club door, turning most of it away. That should feel paradoxical. A black hole is supposed to be the ultimate sink, the ultimate consumer. Yet here we are, describing a system where the dominant behavior might be rejection rather than consumption. The trick is that the energy released by the inner flow can heat the gas enough to launch it outward. Magnetic fields can fling plasma along the field lines. Turbulence can puff the flow up so it does not settle. The gas can gain enough energy that it escapes before it loses its angular momentum. A black hole can sit at the center of a churning, energetic environment that mostly recycles matter back into space. And if that is true, it means Sagittarius A is not only defined by what it swallows, it is defined by what it refuses. This also changes how we think about the relationship between the black hole and the surrounding region. Even when the black hole is quiet in light output, compared to an active nucleus, the outflows can still inject energy into the nearby environment. They can stir the gas, shape magnetic fields, and influence how material moves through the central light years. Quiet does not mean disconnected. Quiet can mean subtle. There is another layer to this story that feels almost personal. The gas feeding the flow does not come from nowhere. It comes from the neighborhood. Massive stars near the center shed material through stellar winds. Clouds drift inward and get stretched. Occasionally something denser wanders too close and gets shredded into streams. The accretion flow is not a steady pipeline. It is a messy supply chain, full of interruptions, clumps, and surprises. That messiness is part of why the system flares. A sudden clump falling in can briefly light up the inner flow. A reconnection event can dump energy into a small region and create a flash. A wobble can change our view and make the brightness seem to pulse. The black hole itself is silent. The plasma around it is noisy, But the deeper you go, the more this becomes a physics story, not just an astronomy story. We are watching charged matter move in a regime where strong gravity and electromagnetism interact. We are watching plasma in curved space-time. We are trying to infer structure from light that has been bent, boosted, and filtered by extreme conditions. Every flare is a clue, and every quiet stretch is also a clue, because it tells us what the system looks like when it is not being disturbed. And now the stage is set for the next question. If the inner environment is this turbulent and this energetic, what happens to the stars living right next door? Not the ones we track as clean points on a plot, but the ones embedded in the dense central region, the ones that should not exist there at all, because the tides from a supermassive black hole should prevent their birth. To understand Sagittarius. A star, we have to understand its neighbourhood, because the neighbourhood is both the fuel source and the witness. When you picture a supermassive black hole, you probably imagine emptiness around it, a lonely dark pit with a thin ring of hot gas, and maybe a few doomed stars skimming the edge. The Milky Way's centre is not like that. It is crowded, violently crowded. The inner few light years hold millions of stars packed into a region that would feel almost unreal if you could stand inside it. The density is so high that compared to our quiet neighbourhood, it is like the difference between a rural field and the floor of a sold-out stadium. If you lived on a planet orbiting a star near the galactic centre, the night sky would be almost too bright to call night. Instead of a few thousand visible stars, you would see an ocean of them. The combined light could be bright enough to cast shadows. It would be beautiful in the way a lightning storm is beautiful, the kind of beauty that comes with danger baked in, because crowding changes everything. In our region of the Milky Way, stars are spaced light years apart. The nearest star to the Sun is more than 4 light years away. Close encounters are rare. Gravitational tugs from passing stars are usually tiny. Planetary systems can remain stable for billions of years. That stability is part of why life has a chance to slowly build complexity. Near the galactic centre, stability is a luxury. Stars pass much closer to each other. Gravitational interactions are common. Orbits get perturbed, systems get rearranged. A planet could spend millions of years in a comfortable orbit, and then, after one unlucky stellar flyby, get thrown into a colder path or a hotter one, or ejected into deep space entirely. Add in the radiation field from many massive stars, plus the occasional X-ray and infrared flares from Sagittarius A star's inner environment, and it starts to look like a place where complex chemistry would have to fight just to survive, never mind thrive. So you might expect the galactic centre to be dominated by old stars, long-lived red dwarfs, ancient stellar corpses, things that have had time to settle into that dense, chaotic dance. And yes, there are old stars there. But here is the problem that makes astronomers sit up straighter. There are also very young, very massive stars right next to the black hole. This is not supposed to happen. The transcript describes a cluster of stars within a few light years of Sagittarius A star that are both extremely massive and surprisingly young. We are talking about O-type stars and Wolf-Rayet stars, some with masses more than 100 times the Sun and ages of only a few million years. These are the celebrities of stellar physics. They burn bright, live fast, and die young. They flood their surroundings with fierce ultraviolet light and powerful stellar winds. Their lives end in dramatic explosions or collapse, leaving behind neutron stars or black holes. The shocking part is not just that they exist, it is where they exist. A supermassive black hole creates intense tidal forces. Tidal forces are the difference in gravity across an object. You already know the gentle version from the moon raising tides on Earth. Near a black hole, that difference can become devastating. If you take a cloud of gas and try to let it collapse under its own gravity to form stars, the black hole's tidal forces can pull the cloud apart before it can finish collapsing. It is like trying to build a sandcastle while someone is constantly raking the sand sideways. In other words, the galactic centre should be a terrible place to make new stars. And yet, there they are. Young, massive, bright, loud. So the central question becomes one of the strangest in the whole Sagittarius A star story. How did these stars get there? There are two main ideas that show up in the transcript, and both are fascinating because both imply a dramatic past. The first idea is that these stars formed in place, inside a dense disk of gas that once existed around Sagittarius A star several million years ago. Picture a thick, heavy ring of gas orbiting the black hole. dense enough that parts of it could collapse into stars despite the tidal forces. That sounds impossible until you remember the gas itself can be massive. If the disk is dense enough, self-gravity can win locally. Stars can form within it, and because the disk is rotating, the newborn stars inherit orbits that share a common sense of direction. Later, the remaining gas disperses, blown out by winds, radiation, or consumed in part by the black hole, and the stars are left behind like footprints after the storm. If that is the correct story, it means Sagittarius A star was surrounded by a serious reservoir of gas in the recent cosmic past. It hints at an episode of feeding, not necessarily a full quasar phase, but at least a period when the centre had far more fuel than it does now. It suggests the quiet we see today may be a temporary mood, not the default state. The second idea is migration. Maybe these stars did not form near the black hole at all. Maybe they formed farther out, where tides are weaker and star formation is easier, and then they moved inward over time. But moving a massive young star inward is not simple. Stars do not drift like dust. They have inertia, they have orbits. To change those orbits, you need interactions, many of them. Gravitational encounters with other stars, friction with gas, the subtle collective pull of a dense stellar environment. In some scenarios, an intermediate mass black hole could have played a role, shepherding stars inward through complex dynamics before being swallowed by the central black hole itself. If the migration story is true, it means the inner galaxy is not just crowded, it is actively rearranging itself. It means the centre has a kind of gravitational conveyor belt, sending some objects inward and flinging others outward. And it implies that what we see today is a snapshot of an ongoing reshuffle. Either way, the young massive stars are not a minor detail. They are evidence. They are a timestamp. Stars this massive do not live long. If they are only a few million years old, then whatever event has put them there happened recently, by galactic standards. While dinosaurs were still a distant future, the Milky Way's centre was already staging a drama that may have involved dense gas disks, violent winds, and gravitational interactions strong enough to move heavy stars through a crowded environment. This also ties back to Sagittarius A star's personality. A quiet black hole today does not mean a quiet centre. The stellar winds from these massive stars pour material into the region. Their radiation shapes the gas. Their deaths will add supernova shocks, neutron stars, and possibly more small black holes. The galactic centre is a feedback machine, where stars feed the environment and the environment feeds the black hole, and the black hole's gravity sets the tempo for everything. So when we ask why Sagittarius A star is underfed, we cannot ignore the fact that its neighbourhood is constantly injecting matter and energy. The question becomes more subtle. It is not just how much material is nearby, it is how that material behaves when it arrives. Does it cool and settle? Does it heat and escape? Does it get trapped by magnetic fields? Does it get launched back out as wind? And the young massive stars add one more twist. If star formation can happen near the black hole under the right conditions, then the galactic centre is not just a place where gravity destroys. It is also a place where gravity, under strange circumstances, can help create. That idea feels almost backwards, and yet the evidence refuses to go away. In the next part, we are going to meet objects that sit right on the line between star and cloud, and that they make this whole region even weirder. They look like gas, they stretch like gas, but they survive like stars. They're called the G objects, and they turn the galactic centre into a mystery box inside a mystery box. If the young massive stars near Sagittarius A star feel like a paradox, the next residents of the galactic centre feel like a prank. Astronomers found objects that look like little clouds of gas and dust, soft-edged and fuzzy, the kind of thing you expect a black hole to shred without hesitation. But when these objects swing past the darkest gravity in the Milky Way, they do not behave like helpless clouds. They survive. They are called the G objects, and they sit in that uncomfortable zone where your eyes say cloud, but their motion says star. They were first spotted as dusty infrared sources near the galactic centre, objects that seemed extended rather than point-like wrapped in warm material. The names sound simple, like inventory tags, G1, G2, up through later discoveries like G3, G4 and beyond. But the behaviour is not simple at all. The most famous is G2. In the early 2010s, G2 became a kind of public science drama because it was predicted to pass very close to Sagittarius A star. If G2 really was just a loose cloud of gas, the expectations were dramatic. The black hole's tidal forces should stretch it into a long stream, feeding material into the inner accretion flow and potentially triggering a bright outburst. People pictured a cosmic meal, a sudden awakening, a flare we could watch with modern telescopes. Then the encounter happened, and nature refused to follow the most dramatic script. G2 did get stretched, it did get distorted, but it did not get shredded into nothing, to merge largely intact, still coherent enough to keep moving as a single object rather than dissolving into a messy spray. Instead of a spectacular feeding event, the galactic center gave us something quieter and far stranger. A thing that looked like a cloud had survived the kind of passage that should have destroyed a cloud. That survival forced a rethink, and it changed the central question. We stopped asking what happens when a gas cloud approaches a supermassive black hole. We started asking what G2 really is. The leading explanation now is both elegant and a little creepy. The G objects are probably not pure clouds at all. They are likely stars, possibly binary stars, wrapped in thick shells of dust and gas that make them look cloud-like in some observations. A star hidden inside would change everything. The gravity of a star can hold on to its surrounding material, keeping the envelope from dispersing completely, even when tidal forces stretch it. The outer layers get pulled and distorted, but the core remains anchored. That idea also explains why the G objects can look extended and fuzzy without behaving like passive gas. They're not just blobs drifting into doom, they are compact systems wearing disguises, moving through an environment where a disguise can be the difference between survival and destruction. But if that is true, it raises a new set of mysteries. Why are there so many of these dusty, wrapped-up objects near Sagittarius A star? What created their envelopes? Are they the aftermath of stellar collisions in a crowded region? Are they the product of binary interactions where stars shed material or merge? Are they linked to star formation episodes near the center? Or are they something else entirely? A class of objects we only notice because the galactic center is the one place where their weirdness becomes obvious. And then comes the darker twist. Even the G objects might not be the strangest hidden residence near Sagittarius A star, because the galactic center is almost certainly full of objects we cannot see at all. Black holes do not need light to matter. Neutron stars do not need to shine brightly to tug on their neighbors. Stellar mass black holes, the remnants of massive stars, could be orbiting in that region like invisible stones in a rushing river. Over billions of years, the galactic center should accumulate remnants. Massive stars form, they die, they leave behind compact objects. In a region as dense as the inner galaxy, those remnants can sink inward through gravitational interactions, slowly gathering into a concentrated population near the supermassive black hole. So picture the scene. Sagittarius. A star at the center. A swarm of normal stars in fast orbits, dusty disguise stars like the G objects, and mixed among them a population of invisible compact remnants, stellar mass black holes and neutron stars that hardly emit anything we can easily spot. It is like trying to understand a dance floor where many dancers are wearing invisible suits, but you still have to predict the collisions. How would we ever know those unseen objects are there? We would see their fingerprints in the orbits of the visible stars. This is where the galactic center becomes a precision physics lab again. When you track stars like S2 and others over many years, you expect their motion to be dominated by the smooth gravity of Sagittarius A star. But if there are additional masses nearby, even smaller ones, they can subtly perturb those orbits. Tiny changes in timing, slight deviations from a clean ellipse, unexpected wobbles, shifts that build up over repeated passages. It is like watching a chandelier sway and realizing the air in the room is not still. The more precisely we measure these orbits, the more we can constrain what else is lurking there. And this is not just about counting invisible objects, it is about testing physics itself. General relativity predicts that orbits near a massive object should precess, meaning the ellipse slowly rotates over time. For S2, observations have already confirmed behavior consistent with that prediction. But future measurements could become sensitive to additional effects, like perturbations from a distributed mass of remnants, or in more speculative scenarios, the gravitational influence of dark matter concentrated near the center. That is the tension that makes the galactic center so addictive to study. Every orbit is both a confirmation and a question. When the orbit matches Einstein, we cheer. When it almost matches, we lean forward. The G objects sit right in the middle of that tension. They remind us that the environment near Sagittarius A star is not a clean two-body system. It is a crowded arena where stars evolve under stress, where envelopes of dust can form and persist, where close encounters may reshape objects into forms we do not see elsewhere, and where invisible masses may be quietly rearranging the whole scene. And there is a deeper emotional point hiding under all this technical detail. The galactic center is not a static photograph. It is a living ecosystem of gravity. Objects form, migrate, collide, lose mass, gain mass, get stripped, get wrapped, get thrown outward, or get pulled inward. Some survive in surprising ways. Some vanish without a flare, and all of it happens on timescales that are slow for humans but fast for a galaxy. Which brings us to a looming, brutal possibility. In this crowded environment, it is not a matter of if something gets too close. It is a matter of when. Dusty objects like the G family will keep returning. Stars will keep being nudged into riskier orbits. Remnants will keep drifting. Eventually, one object will cross the wrong line and the black hole will not just distort it, it will tear it apart. In the next part, we are going to look at what that destruction actually means, not as a metaphor, but as a physical process. The moment a star becomes a stream, and the galaxy's quiet giant briefly becomes a lighthouse. There is a reason the word tidal feels so harmless. It makes you think of beaches, moonlight, slow water rising and falling. Near a supermassive black hole, tidal forces are the opposite of gentle. They are the difference in gravity between the near side and the far side of an object. And when that difference becomes extreme, the object stops being an object. It becomes a process, a stretching, a tearing, a long, luminous undoing. Imagine a star on a bad trajectory. It wanders inward on an orbit that brings it too close to Sagittarius A star. Far away, the black hole's gravity is not special. Close in, the gradient becomes savage. The near side of the star feels a much stronger pull than the far side. The star is no longer held together by its own gravity in the same way. It starts to elongate, pulled like taffy, forming a stream of hot gas. This is what astronomers call a tidal disruption event. The phrase is clinical. The reality is violent. At the critical distance, the star crosses a threshold where it cannot remain intact. It is stretched into a long ribbon. Part of the stellar material gains enough energy to be flung outward, escaping into space at high speed. The rest loses energy and falls inward, joining the black hole's feeding flow. And when that material crashes into the inner region, it heats up to insane temperatures and releases a burst of radiation that can be seen across vast distances. In other galaxies, tidal disruption events have been observed. They are rare, maybe once every 10,000 to 100,000 years per galaxy on average, but when they happen, they can flare so brightly they briefly rival the light of the entire host galaxy. They are like a cosmic alarm bell, a sudden moment when a quiet black hole becomes impossible to ignore. The strange thing is that we have not seen a clear tidal disruption event happen at the Milky Way's center in recorded human history. That does not mean it has not happened. It means we have been watching for a blink of time compared to the galaxy's schedule. The odds of catching one in any given year are small, but over decades the odds rise, and our ability to detect these events has improved dramatically. This is where the tension becomes real for modern astronomy. Sagittarius. A star has a crowded neighborhood. Stars are constantly being nudged by gravitational interactions. Some stars that look safe can get perturbed into more elongated orbits. Some can be sent inward, some can be thrown outward entirely. In a dense stellar environment, it is not unusual for orbits to be shuffled like cards. The black hole does not need to hunt, the crowd delivers. We also have the G objects, those dusty, disguised systems that keep making close passes. Most have survived so far, but survival is not guaranteed forever. If an object's envelope is thinner than expected, or if the hidden star is smaller or less able to hold itself together, one close passage could end differently. The tidal forces do not negotiate. They wait for a weakness, and then there is a darker population we cannot easily see. Stellar mass black holes, neutron stars, compact remnants. These can perturb orbits too. They can act like invisible billiard balls, changing trajectories in subtle ways. The more crowded the center is, the more opportunities there are for something to be shoved onto a fatal path. So when will the Milky Way's next tidal disruption event happen? We do not know. It might happen tomorrow, it might not happen for 10,000 years. That uncertainty is not a failure of science. It is a feature of a chaotic system. But what matters is this. If it happens in the era of modern telescopes, we will have a front row seat. We would see the star distort. We would see the light curve rise and fall as the shredded material forms a temporary accretion flow. We would watch the spectrum change as the gas heats and cools. X-ray telescopes would pick up the hottest region. Infrared and optical instruments would track the cooler expanding debris. Radio telescopes could detect outflows and shocks as the event interacts with surrounding gas. And those observations would not just be fireworks for our curiosity. They would answer deep questions about how black holes feed. Right now, Sagittarius A is quiet because most inflowing material seems to get kicked back out. A tidal disruption event is different. It delivers a sudden, dense supply of material deep into the inner region. It is a stress test for the entire feeding ecosystem. It tells us how quickly a black hole can switch from sipping to feasting, and what role magnetic fields and winds play when the fuel supply becomes overwhelming. There is another reason tidal disruption events matter. They are natural laboratories for relativity in action. As the debris stream swings around the black hole, its path is shaped by curved space-time. The most bound material returns toward pericenter again and again, forming a changing flow that can precess. The inner region can be warped by frame dragging if the black hole is spinning. The light emitted close in is lensed, boosted, and time delayed. In the right event, we could potentially observe signatures that let us test models of accretion and space-time geometry in ways that are normally impossible. And then we hit the haunting question behind the spectacle. What happens to a star in a fundamental sense when it crosses the event horizon? All the light we see from a tidal disruption event comes from outside the horizon. The star is torn apart, yes, and half the gas falls inward, yes, but the moment that gas crosses the boundary, it stops talking to the universe. No signal escapes, no update, no final message. From the outside, it is like watching a story whose last page has been ripped out, which is exactly why black holes sit at the center of one of the deepest problems in physics, the information paradox. Because in quantum mechanics, information is not supposed to be destroyed. In principle, the universe keeps a perfect record. If you knew the complete quantum state of a system at one time, you could evolve it forward or backward. The equations do not delete, they transform. A black hole feels like deletion. Throw something in and all the detailed information about its state disappears behind the horizon. You can keep track of mass, spin and charge, but the rest seems gone. If the black hole lasts forever, maybe the information is just hidden. But black holes do not last forever in theory. They radiate slowly. Over unimaginable time, they can evaporate. So here is the nightmare version of the story. A star falls in. The black hole later evaporates away into radiation that looks like random heat. Where did the information go? That question is not philosophical fluff. It is a direct collision between general relativity and quantum mechanics, our two best theories of nature. They both work incredibly well in their own domains. Black holes force them to share the same room, and when they do, they start arguing. Sagittarius, a star, is our closest stage for that argument. We cannot see inside, but we can observe the edge, and the edge is where the universe seems to be hiding its rules. Every flare, every orbit, every potential tidal disruption event is a chance to learn how this boundary behaves in reality, not just in equations. So the next step in our journey goes beyond us and gas and magnetic fields. We are going to follow the logic of Hawking radiation, the strange quantum effect that says black holes are not perfectly black and the paradox it creates, because the dark heart of the Milky Way does not just hold our galaxy together. It holds a mystery that might rewrite what we think reality is made of. Black holes feel like the ultimate act of cosmic finality. Something crosses the event horizon, and that is it. No signal returns, no light escapes, no last words. For a long time, it was tempting to treat a black hole as a perfect vault, a place where information can be hidden from the rest of the universe forever. Then physics pulled a trapdoor. In the 1970s, Stephen Hawking showed that black holes are not perfectly black. Even without swallowing anything new, a black hole should emit a faint glow, not because light climbs out from inside, but because quantum physics refuses to let empty space be truly empty. Quantum mechanics says that the vacuum is restless. Space is filled with fluctuations, tiny temporary pairs of particles and antiparticles that pop into existence and vanish again almost immediately. In ordinary conditions, they annihilate each other so quickly you never notice. But near an event horizon, the geometry of space-time changes the rules of the game. The boundary becomes a kind of referee, splitting what would have been a fleeting private quantum event into a public outcome. Here is the simplified picture. A particle pair appears right at the edge. One member of the pair ends up just outside the horizon. The other ends up just inside. The one inside cannot escape. The one outside can. From far away, it looks like the black hole has emitted a particle. But energy cannot come from nothing, so the cost is paid by the black hole itself. The black hole loses a tiny bit of mass. That faint emission is what we now call Hawking radiation, for a black hole like Sagittarius. A star, this radiation is absurdly weak. It is so weak that it is completely drowned out by the environment. The Milky Way's center is full of dust, plasma, stars, and energetic processes that produce far more radiation than Hawking radiation ever could. Even the cosmic microwave background would overwhelm it. So this is not a practical observational effect for our galactic center. Not today, but as an idea, it is dynamite. Because Hawking radiation implies that black holes can evaporate, very slowly for supermassive ones, fantastically slowly, on timescales so long they make the age of the universe look like a short nap. Still, in principle, if a black hole were isolated and not fed new matter, it would gradually lose mass and shrink away, and that creates a paradox sharp enough to cut through decades of physics. Quantum mechanics is built on a principle that information is preserved. The exact phrasing depends on how deep you go into the math, but the core intuition is simple. The universe does not delete details. If you know everything about a system now, the laws of quantum mechanics allow you to evolve that system forward in time without losing the full story. You can scramble it, hide it in correlations, disperse it across the room, but you do not destroy it. A black hole seems to do exactly that. Throw in a book, a star, a planet, a whole library, and from outside all you can measure afterward is the black hole's mass, spin, and charge. The detailed information about what fell in appears to be gone from our universe. For a while you could dodge the problem by saying the information is still there, just trapped behind the horizon, hidden, not destroyed. But Hawking radiation ruins that escape hatch. Hawking's original calculation suggested that the radiation is thermal, like heat from a hot object. Thermal radiation is bland, it looks random, it carries no obvious imprint of the detailed quantum states of everything that fell in. So if the black hole evaporates completely into this radiation, it looks like the information has been erased, not hidden, destroyed. That is the black hole information paradox, and it is not a niche headache for theorists. It is a direct clash between our two most successful descriptions of nature. General relativity says event horizons are real causal boundaries. Quantum mechanics says information cannot be destroyed. Both frameworks are incredibly well tested, but they cannot both be completely right in the black hole regime without something subtle happening. So what is the universe doing? Several broad families of ideas have emerged, each with its own weirdness tax. One possibility is that the information is encoded in the Hawking radiation after all, not in obvious labels, but in extremely subtle correlations between the emitted particles. In that view, the radiation is only approximately thermal. If you could measure the full quantum pattern perfectly, you would find the missing story hidden in the correlations. The black hole would behave like a cosmic encryption machine. It would not delete information, it would scramble it. Another possibility is that the information comes out in a dramatic way at the very end of evaporation, when the black hole becomes small. But that raises problems, because it would require a tiny final remnant or a sudden release of an enormous amount of information, both of which come with theoretical difficulties. Another possibility is that the event horizon is not as simple as we think. Maybe it has quantum structure, maybe the boundary is fuzzy, maybe what we call the horizon is a classical approximation, and in reality the edge has microscopic degrees of freedom that store information and then re-emit it over time. Different approaches give different names to that idea, but the vibe is the same. The horizon is not a passive line, it is an active system. And then there are more radical proposals that suggest our classical picture of smooth spacetime breaks down in ways that change the story entirely. Some of these ideas get controversial fast because they can imply violent effects near the horizon that would challenge another cherished belief, the idea that an observer falling into a large black hole should not experience anything special exactly at the horizon. That belief is called the equivalence principle in spirit, the idea that locally physics looks normal in freefall. Many physicists are reluctant to give that up, so the paradox becomes a three-way standoff: information preservation, smooth horizons, and standard quantum field behavior. Many arguments suggest you cannot keep all three in their simplest form. Something has to bend. And this is where Sagittarius A star becomes more than a galactic curiosity. It becomes a nearby symbol of the limit of our understanding. We cannot test Hawking radiation from it directly, but we can study how real black holes behave at their edges. We can measure spins, we can map magnetic fields, we can track matter orbiting close to the point of no return, and we can test general relativity and strong gravity. Every observation helps constrain what kinds of quantum gravity theories are even plausible. Think about how strange this is. The dark heart of our galaxy is helping us interrogate the deepest rules of reality, not by giving us answers, but by refusing to be simple. And once you start thinking this way, another idea appears almost inevitably, an idea that is even stranger than Hawking radiation, and it grew out of the same logic. The idea that the information content of a region of space might be encoded not in its volume, but on its boundary. The universe is a kind of hologram. That is where we go next. The information paradox is unsettling because it does not feel like a small mistake. It feels like a crack in the floor. Either black holes destroy information, which would shake quantum mechanics, or information escapes in a way we do not yet understand, which would mean the event horizon is not the simple boundary we thought it was. And once you accept that horizons might be special, another strange idea starts to look less like science fiction and more like a clue. It is called the holographic principle. The simplest way to feel it is to ask a question that sounds innocent. How much information can you pack into a region of space? Not books on shelves, but fundamental information, the number of possible distinct physical states that region can contain. Your instincts say the answer should scale with volume. A bigger box holds more stuff, so it holds more information. But black holes do not play by that intuition. If you keep cramming matter and energy into a region, eventually it collapses into a black hole. That collapse creates a limit. You cannot pack unlimited information into a finite space because gravity will step in and say no. Now comes the weird part. When physicists calculate the maximum information content before collapse, the answer does not scale with the volume of the region. It scales with the area of its boundary. Area, not volume. That is the first punchline. It is as if the universe is telling us that the deepest bookkeeping of reality is written on surfaces, not in interiors. For a black hole, the event horizon acts like that surface. The horizon has an area, and that area corresponds to an entropy, which is a measure of how many microscopic states could produce the same macroscopic black hole. That entropy scales with horizon area, not the volume inside area, so the black hole behaves like a kind of cosmic hard drive whose storage capacity is proportional to its surface area. If you find that idea strange, good. It is strange. It is one of the strangest clues modern physics has ever stumbled over, and it keeps surviving serious scrutiny. Now connect that back to the information paradox. If information is not truly lost, it has to be stored somewhere. If the horizon area counts the number of possible internal states, then the horizon might be the place where information is encoded. Not deep inside the black hole in a hidden vault, but on the boundary itself in a way that preserves quantum rules. In that picture, the event horizon is not a featureless line. It is a physical system with microscopic structure, even if we cannot see that structure directly. That idea leads to the more mind-bending version of holography. Maybe the information describing everything inside a region is fully encoded on the boundary of that region, like a hologram on a card that looks three-dimensional when you tilt it, even though the pattern itself is two-dimensional. The three-dimensional scene is not literally sitting inside the card, but the information needed to reconstruct it is encoded on a surface. If you let that sink in, it starts to sound like an attack on common sense. But physics has never promised to be friendly to common sense. It promised to be consistent. There is a famous mathematical example that made many physicists take holography seriously, not as poetry but as machinery. It is called the anti-de Sitter and conformal field theory correspondence. In that framework, a theory of gravity in a particular kind of curved space can be equivalent to a quantum theory without gravity defined on the boundary of that space in one fewer dimension. The details are technical, but the implication is wild. A gravitational world can be fully described by a non-gravitational world living on its edge. That is not just a metaphor, it is a true equivalence in the mathematics of certain models. Now, our universe is not exactly that kind of space, so we should be careful. This is not proof that reality is literally a hologram in the everyday sense. It is a working theory, a framework, an existence proof that holographic descriptions can be real, consistent, and useful. What it tells us is that the idea is not nonsense. The universe can, under the right conditions, allow a boundary description that contains everything. So why is this relevant to Sagittarius A star? Because black holes are the places where holography first grew teeth. Every black hole has a horizon area. Every horizon area implies an entropy. Every entropy implies a finite number of microstates, a finite information capacity. So the event horizon of Sagittarius A star, enormous as it is, would represent a vast but finite information budget. The black hole is not an infinite sink in the information sense. It is an object with a measurable capacity, at least in principle. And once you start thinking like that, the event horizon stops being a passive point of no return. It starts looking like an interface. A boundary where deep physics happens. A place where quantum mechanics and gravity negotiate their terms. This is why the phrase dark heart feels appropriate. Not because the black hole is evil, but because it hides the internal story behind a boundary we cannot cross. Yet paradoxically, the boundary itself might be telling the story in coded form. There is another way to appreciate holography that feels less abstract. Imagine you are trying to describe a room. You might think you need all the points inside the room to specify everything, but holography suggests you might be able to encode the full description on the walls in a way that still allows the interior to emerge as an effective reality. Not an illusion, but an emergent description. Like temperature is real even though it emerges from the motion of atoms. That word emergent is important. It is possible that space-time itself is emergent, not fundamental. Gravity could be an effective description of deeper quantum information dynamics. If that is true, black holes are not just objects in space-time. They are stress tests for the very idea of space-time. And that brings the story back to what we can actually observe. We cannot read the microstates of Sagittarius A star's horizon. We cannot decode the information bookkeeping directly, but we can study the boundary region where these ideas should leave footprints. We can track stars in tight orbits and see whether relativity behaves exactly as predicted. We can image the shadow and test the geometry of light bending. We can measure polarization patterns that reveal magnetic structure close to the horizon. We can watch flares that happen on timescales suggesting emission from the innermost region. Every one of these measurements is a constraint on what the horizon can be. Think of it like this. If the event horizon has quantum structure, that structure should not allow arbitrary behavior. It must still produce the clean classical physics we see at large scales. It must preserve information in a way consistent with quantum rules. It must reproduce the shadow shape and the orbital dynamics. It must agree with the quietness and the flares, the observational facts of Sagittarius. A star are the guardrails that stop theory from becoming fantasy. So holography is not a punchline. It is a compass direction. It suggests that the solution to the information paradox may involve treating the horizon as a carrier of information. It suggests that the interior might be encoded on the boundary in a way that preserves quantum mechanics. It hints that space-time might be an emergent concept built from deeper information relations, and it turns black holes from monsters into messages, strange objects that may be telling us what reality is made of. Now here is the twist that makes this feel almost poetic. We are not studying some distant abstract horizon. We are studying our nearest supermassive black hole, a real object, sitting at the center of our galaxy, quiet most of the time, occasionally flaring, surrounded by stars running on relativistic leashes, imaged as a shadow ring against glowing plasma, all of it happening whether we understand it or not. And the next question becomes unavoidable. If black holes sit at the intersection of gravity, quantum mechanics, and information, then what else can they tell us about the universe beyond our galaxy? About how black holes grow, how galaxies evolve, and how the cosmos changes over time. That is where we go next, by zooming out from our local dark heart to the population of supermassive black holes across the universe, and seeing what Sagittarius A star teaches us about them all. Once you zoom out far enough, Sagittarius A star stops being a single mysterious object and starts looking like a representative of a much bigger pattern. Most large galaxies appear to host a supermassive black hole in their centres. Not a few rare galaxies, most of them. It is as if galaxy formation and black hole formation are tangled together, growing side by side, feeding each other, and occasionally punching each other in the face. That last part is not a joke. The relationship is not gentle. When a supermassive black hole is actively feeding, the energy response can be staggering. Matter falling into a black hole can convert a surprisingly large fraction of its mass into energy before it disappears, far more efficient than the fusion that powers stars. That energy does not just vanish into the event horizon. Much of it is radiated outward as light, and much of it drives winds and jets that slam into the surrounding gas. This is called feedback, and it is one of the reasons black holes matter far beyond their immediate neighbourhood. Feedback can work like a thermostat. The black hole feeds on gas, then the energy release heats and pushes that gas away, which reduces the supply, which slows the feeding. It is a self-regulating loop. But that loop does not just regulate the black hole, it regulates the galaxy. If gas is blown out or heated up, it cannot cool and collapse to form new stars. Star formation slows down. In the most extreme cases, black hole activity can help turn a star-forming galaxy into a quiet galaxy full of old stars. That is why some of the most massive galaxies in the universe are full of red, aging stellar populations. Their central black holes likely went through powerful active phases that pushed out the cold gas and shut the factory down. The Milky Way is not in that phase today. We are still forming stars. Sagittarius. A star is not a blinding active nucleus. It is quiet, but quiet now does not mean quiet forever, and it does not mean quiet in the past. There is evidence in our own sky that the Milky Way's central black hole was more violent not long ago in cosmic terms. The most dramatic example is the Fermi bubbles. They are enormous lobes of high-energy emission that extend above and below the plane of the galaxy. Each one is on the order of 25,000 light-years across, towering like ghostly pillars on a scale comparable to our distance from the galactic centre itself. They shine primarily in gamma rays, which tells you immediately that they are filled with extremely energetic particles. The edges of these bubbles are unusually sharp. That detail matters. If the bubbles had inflated slowly and gently, you would expect them to fade gradually into the surrounding gas, with soft boundaries where everything mixes. Sharp edges suggest something more explosive, a powerful outflow that carved a clear boundary into the galactic halo. So what could have launched an outflow powerful enough to inflate structures that large? One leading explanation is a past feeding event at Sagittarius A star, a period when the black hole consumed far more material than it does today. When a supermassive black hole accretes rapidly, it can drive winds and sometimes jets that channel enormous energy outward. Over millions of years, that energy can inflate bubbles in the surrounding medium, accelerating particles and creating the gamma-ray glow we see now. The energy budget implied is huge, often compared to something like 100,000 supernova explosions worth of energy. Whether that comparison is exact depends on models, but the point is the same. This was not a small burp. This was a major episode. There are also structures seen in X-rays that appear to connect the galactic center to the base of the bubbles, sometimes described as chimneys. Think of them as channels where hot gas and energy may have flowed outward during the active phase. Add to that the strange radio filaments and arcs near the galactic center, long thin threads of synchrotron emission that reveal energetic electrons spiraling along magnetic field lines. The region looks like it has been stirred, magnetized and energized in ways that fit naturally with a history of outbursts. The timing is part of what makes this feel immediate. Estimates often put the bubbles at roughly 6 to 10 million years old. That is recent on a galactic clock. It means the Milky Way's center may have looked dramatically different, while early human ancestors were still far in the future. For a brief window, the heart of our galaxy may have been much brighter, much more active, perhaps even visible as a dominant feature in the sky from many vantage points within the Milky Way. So Sagittarius A star becomes a lesson in phases. Quiet is a phase. Active is a phase. The galaxy remembers. This is also where the story of our local black hole ties back into the big cosmic story. When astronomers survey the universe, they see black holes at every activity level. Some galaxies host blazing quasars that can be seen across billions of light years. Others host quiet nuclei with faint radio or X-ray signatures. Some show jets that stretch far beyond the visible galaxy. Others show subtle winds and turbulence. The differences are often about fuel and timing, not about some fundamentally different kind of black hole. In that view, Sagittarius A star is not an oddball. It is an example of what many supermassive black holes are doing right now, waiting, sipping, flickering, keeping its spin and its magnetic structure like a coiled spring. And that brings us to a question with teeth. How often do galaxies go through these active episodes? Are they rare once per 100 million years events? Or are they more common, repeating every few million years in smaller bursts? The truth may vary from galaxy to galaxy. It may depend on mergers, on gas inflows, on star formation cycles, on how often dense clouds make it to the centre. But Sagittarius A star offers a nearby case where we can search for the smoking guns of past activity and connect them to physical mechanisms. It also reframes the emotional meaning of the black hole. A supermassive black hole is tiny compared to its galaxy. Sagittarius. A star is an almost comically small fraction of the Milky Way's total mass, yet its influence can reach tens of thousands of light years if it becomes active. That is the recurring theme of black holes: small object, massive consequence. Now here is the part where the universe gives us a gift, because we are not just looking backward, we are looking forward. The next generation of observations aims to turn that single portrait of Sagittarius A star into motion. The goal is not just sharper images, the goal is movies, watching bright structures orbit and evolve close to the event horizon on our timescales. More telescopes in the Event Horizon Telescope network improve resolution and coverage. Better algorithms improve reconstruction. Polarization measurements improve magnetic mapping. Multi-wavelength monitoring lets us connect flares in X-rays and infrared to changes in radio emission. We are slowly turning Sagittarius A star from a mysterious dot into a dynamic system we can track, and every improvement matters because it tightens the cage around theory. If general relativity is correct, the shadow and lensing behavior should follow specific rules. If the accretion flow is magnetically dominated, polarization should reveal it. If spin is high, the inner dynamics should show signatures consistent with frame dragging. If something about the horizon is more exotic than classical physics suggests, we might find tiny deviations in orbital precession, subtle shifts in timing, unexpected structure in the variability. We are not guaranteed a revolution, but we are guaranteed better constraints, and constraints are what turn wild ideas into science. So by the end of this part, the Milky Way's dark heart has changed shape in our minds. It is not merely a monster that swallows, it is an engine that sometimes breathes outward. It is a regulator of galactic ecology. It is a historical record of past outbursts written across the sky in gamma rays and magnetic filaments. And it is a nearby boundary condition for our deepest theories about space-time and information. In the final part, we are going to bring this journey home in two directions at once. We will look outward to the far future of our galaxy, including the eventual collision with Andromeda and what that means for the black holes at both centres. And we will look inward at what it means that a small species on a small planet can measure a shadow 26,000 light years away and use it to question the nature of reality itself. There is something almost unfair about Sagittarius A star. It sits 26,000 light years away, hidden behind dust, invisible in ordinary light, and yet it shapes the story of our galaxy like an anchor you cannot see. It was there long before the sun formed. It will be there long after the sun is gone. And while we argue about daily headlines and short-term problems, the Milky Way keeps turning, slowly, steadily, carrying us around a dark centre that does not care what we call it. But the galaxy is not eternal in its current form. In the far future, the Milky Way has an appointment. Andromeda is coming. Right now it's about 2.5 million light years away and approaching us at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide. That word collide is misleading if you imagine star-on-star crashes like billiard balls. Even in a galactic collision, individual stars almost never hit each other directly. Space is too empty. The galaxies interpenetrate like swarms, their stars weaving through without direct contact. What changes everything is gravity. As the Milky Way and Andromeda pass through each other, their gravitational fields will distort and stretch both systems. Tidal forces on galactic scales will fling stars into new orbits, pull out long streams, and reshape spiral disks into something more chaotic. Gas clouds will slam into each other far more often than stars do, compressing and triggering bursts of star formation. The night sky for any observers alive then would be stunning and terrifying, filled with huge arcs of light, new star clusters igniting, and the familiar pattern of the Milky Way's band dissolving into a different shape. And at the centres of both galaxies sits the real drama. Andromeda has its own supermassive black hole, likely far larger than Sagittarius A, with a mass on the order of 100 to 200 million solar masses. When the galaxies merge, their central black holes will not instantly collide. First, they will sink toward the centre of the newly forming combined galaxy through dynamical friction. As each black hole moves through the sea of stars and gas, it gravitationally perturbs that material and loses momentum, spiralling inward. Over millions of years, the two black holes will form a bound binary orbiting each other. In this phase, the surrounding environment becomes a cosmic slingshot. Stars passing too close can be flung outward at enormous speeds, sometimes fast enough to escape the galaxy entirely. The binary acts like a gravitational machine that converts orbital energy into ejections. Then the final mechanism takes over. Gravitational waves. When the two black holes get close enough, they begin to lose energy by radiating ripples in space-time. Their orbit tightens, they spiral faster. The final moments become absurd, two event horizons circling each other at significant fractions of the speed of light, space-time itself ringing with an energy release that would dwarf many other cosmic events. Then the horizons merge into one, and a single larger black hole is born, carrying the combined mass minus a fraction radiated away as gravitational waves. This is not just a future fireworks show, it is the fate of our galactic centre. The merge system is often nicknamed Milkomeda, the blended remnant of the Milky Way and Andromeda. Over time, it is expected to become a more elliptical galaxy, less like a graceful spiral and more like a smooth glowing oval. At its heart, a larger black hole will sit where Sagittarius A sits today, but much more massive, a new dark heart for a new galaxy. And here is one of the strangest wrinkles. The merger can be asymmetric. If the spins of the black holes are misaligned, or if their masses differ enough, the gravitational wave emission can be uneven. That unevenness can give the merged black hole a recoil kick, launching it away from the centre. In extreme cases, a merged black hole could even be ejected from a galaxy. Whether that happens in Milkomeda depends on details we cannot predict yet, but the possibility is real in the physics. So the far future includes a moment when the central darkness might literally wander. Now zoom back in from billions of years to decades and centuries, because for us, the near future is where the story becomes personal again. In the short term, Sagittarius A will likely remain quiet most of the time. It will continue to sip, it will continue to flare occasionally, but the odds that we catch something dramatic are not zero. A tidal disruption event could happen while we have instruments watching. A dense cloud could drift inward and trigger a brighter active phase. A small black hole could merge into the central one, producing gravitational waves at frequencies future detectors might capture. These are low probability in any given year, but the universe does not need to be frequent to be consequential. It only needs to happen once while we are looking, and we are building better eyes. The Event Horizon Telescope is expanding, adding more stations, improving coverage and aiming for higher frequency observations that can see deeper into the environment near the horizon. The long-term dream is to make movies, to watch the plasma swirl around Sagittarius A in real time, tracking bright spots and changes hour by hour. On the infrared and optical front, adaptive optics continues improving, allowing more precise stellar tracking and the discovery of more stars on tighter orbits. X-ray observatories continue monitoring flares and hot gas. Polarimetry improves our view of magnetic geometry. Gravitational wave astronomy is growing, with future space-based detectors designed to listen to lower frequency waves, the kind made by supermassive black hole mergers. This is what makes the present era feel like a threshold. We are shifting from inference to imaging, from static measurements to dynamic, from a handful of stars to a full orbital sensors, from a single portrait to a movie. But the deepest reason Sagittarius A matters is not only because it is a spectacular object, it is because it stands at the boundary of knowledge. Black holes force us to confront questions that ordinary environments never ask loudly enough. What is space-time? Is it fundamental or emergent? What happens to information? How can quantum mechanics and gravity both be true in the same place? Is the event horizon a smooth boundary or a quantum interface? Are our best theories complete or just powerful approximations? Sagittarius? A star does not answer these questions directly. It does something more interesting. It pins them to reality. It says, whatever your theory is, it must fit this. It must fit the shadow size. It must fit the stellar orbits. It must fit the flares and the quietness. It must fit the magnetic structure implied by polarization. It must fit a universe where black holes exist not as mathematical curiosities, but as common working parts of galaxies. And there is a human story behind that. Andrea Ghez and Reinhard Genzel and their team spent decades tracking stars through dust and turbulence, turning faint infrared points into a gravitational map. Hundreds of scientists and engineers built and operated the Event Horizon Telescope, coordinating observatories across Earth, aligning clocks, moving petabytes of data, and reconstructing an image from signals that were never meant to become a picture. That collaboration is what science looks like when the universe refuses to cooperate. Not lone geniuses, communities, patience, arguments, iteration, grad students and telescope operators and software developers and theorists all pushing against the same mystery. And then comes the quiet, almost emotional payoff of the whole journey. We live far from the galactic center, out in the suburbs of the Milky Way. That's probably good, because the center is chaotic and harsh. Yet from this quiet corner, we can still reach it with our minds and our machines. We can measure a black hole's mass by watching stars orbit an invisible point. We can photograph a shadow shaped by the warped space-time. We can use that shadow to challenge our understanding of reality. A species on a small planet is doing astrophysics on a monster that could swallow our entire solar system without noticing. That is not just knowledge, that is a kind of cosmic audacity. So the biggest secret of the Milky Way's dark heart may not be any single fact about Sagittarius A star. It may be what Sagittarius A star represents, a place where the universe shows its most extreme behavior openly enough for us to test, but privately enough to keep its deepest rules hidden. A teacher that speaks in orbits, shadows, and flares, forcing us to keep refining what we think we know. And as long as we keep asking, the story does not end. It deepens. The shadow stays there, 26,000 light-years away, ringed by light, holding together the dance of hundreds of billions of stars waiting for the next discovery and for the next generation of minds curious enough to chase it.